Here we go. Welcome in. Nice to see you all back again. Now we're talking about min-max values, something you should feel very comfortable with in calculus. Let's do it. So out here, folks. Sorry, I got stuck something. Here we go. So if something's called a max, then we know that for any point in the neighborhood surrounding this, it's got to be lower than that point. Same with min. If I have a min at AB, that means any coordinate in the neighborhood surrounding AB has to be higher than AB. And so we will see that if I have a local min or max, that my x-word derivative is 0 and my y-word derivative is 0. This means my z versus x slope is 0 and my z versus y slope is 0. Let's just do this first example and we can kind of talk about these situations as well. Okay, let's see what we got here. I need to take the partial derivative with respect to x, set it equal to 0, partial derivative with respect to y, set it equal to 0, and see if I need to kind of leverage those against each other to get a final answer. F sub x would be 2x, nothing, minus 2, done. And so I know that that's going to make 0 when x equals 1. That one should be pretty straightforward. I do the same thing for y, f sub y. F sub y is going to be 2y minus 6 and gone equals 0. That means y equals 3. And so then I have this kind of coordinate 1 comma 3 comma blank. I have to fill in that blank, and I also have to kind of quantify that as a min or a max. Now, personally, I'm looking at this thinking this is a positive upward facing parabola. This is a positive upward facing parabola. I could also be thinking, hey, my slopes go from negative to positive. My slopes go from negative to positive as they cross over these. So this should be a min. It should be a min. But let's just go double check it. I plug in 1 squared plus 3 squared minus 2 minus 18 plus 14, and I get my final coordinate here of 1 comma 3 comma 4. And that should be a minimum. Let's take a moment and look over at Desmos 3D to see that minimum in action. Kapow, right there. And again, what I want to show is when I eliminate x, this is just a happy face parabola. It's probably shifted over a little bit, 3 spaces I would say, based on completing the square, and then raised in the same way. If I eliminate y and I just have x and z in my view, I still see that upward happy face parabola coming from that positive x squared, that positive y squared. And so let's just keep going. Let's try another example, because again, like it says, you have to picture the shape, right? When I see z versus positive x squared and z versus positive y squared, my traces are looking like this, so I know it's going to be a minimum. But when I flip to this one, you can already see the problem. When I do z versus y, I'll end up with a happy face parabola. When I see z versus x, I'd see that a value downwards parabola. We could still find an extreme value though, because I should still have a vertex of this parabola and a vertex of that parabola. Maybe they coincide, maybe they don't. Maybe one is a min and one is a max. Let's see, let's just take a look and see what happens again. F sub x would be negative 2x equals 0. That means x equals 0. F sub y would be 2y equals 0, which would mean y is equal to 0. And that would give me the coordinate 0, 0, 0. But that's my issue. If this is 0, 0, 0, and this is 0, 0, 0, how could it be a min and a max at the same time? So again, like if I'm thinking about, this goes from negatives to positives. This goes from positives to negatives. See, that's what happens when somebody barges into your room when you're recording a video. All of a sudden you pause and you completely lose track of where you are. We're saying that this is not quite a min, not quite a max, and it's a little bit of both at the same time. So let's hop over to Desmos 3D and see what the image of this function looks like. Y squared minus x squared Looks like a pair of pants, obviously. That's what we've come to expect at this point, right? And then this is ultimately, right, a hyperbola from above, square minus a square, a parabola on zx, and a parabola on yz. So this special point in here, where I have both a min and a max happening at the same time, is called a saddle point. A saddle point is a min in one direction, a max in the other direction, and that's why we get zeros for the derivative, because I still have that flat zero tangent, and I still have that flat zero tangent, but they're facing, that's like, it's concave up, concave down, kind of a disagreement there. So we will find a test that shows us kind of when all three of these things happen, and it's right over here. It's from taking a determinant of a matrix. And I don't want to overwhelm you with too much information. I just kind of want to give it to you and hope that you believe me here, that there's a special matrix called the Hessian. And the Hessian is where I take f. It's like I'm going to take f sub x, and I'm going to take its x derivative and its y derivative. Then, for my second row and my second function, I'm going to take f sub y, and I'm going to do the same thing, just in the other order. And so now, when I do this cross product, I get my second derivative with second partial with x times my second partial with y minus xy times yx. And as we learned, or as we've just grown to understand, these are equal. As long as I'm continuous in this region, these are equal. So I've got this f double x, f double y minus this thing squared. And if it's easier to compute yx, you're allowed to compute yx instead. But it's interesting what happens here. This is kind of a concavity check, where if this is a positive upward concavity, and this is a positive upward concavity, it's very likely to be a minimum. Whereas if this is a concave down and a concave down, this would also come out positive. So when I'm multiplying this negative negative or positive positive, right, we're going to end up with some weird things coming out of it when this changes. I'm not getting my words of concave up. It's concave down when I have a second derivative that's negative. And if d is positive, that means my second derivative overcomes this term. And so what we need to do is we need to grow and understand exactly what this term is. I like to call this term twist, because we're taking an x-word derivative and a y-word derivative. So we're kind of twisting, where this is just x by x acceleration, y by y acceleration. This is x by y. This is both directions at once. And so if I have a situation where my twist is greater than my concavity, I have a saddle point. So I'm going to do this calculation. I'll get this value out d, and I'll compare this d. If this d is positive, concavity overcomes twist. And therefore, I'm going to check what my concavity is. If it's 0, it's inconclusive. This rarely, if never, happens. Next is d is less than 0. That means this term was greater. My twist overcomes my concavity, and I have a saddle point. Especially since this would be probably positive, negative, or negative, positive, and it would be a negative and another number, and just definitely negative. That's kind of what we're looking at here, folks. Let's do a couple of examples together where we find some min-max points. We're going to find a shortest distance as well, and then a nice word problem to finish us up. Here we are looking at this one. Find the min-max and saddle of this function. All right. I need my f sub x, which in this case is 4x cubed minus 4y. This is like get a little tricky, huh? Because when I go to solve for x, it gets solved in terms of y. Well, let me try y. Let me try y. F sub y is that's going to work out to be the same thing, isn't it? This is going to be 4y cubed minus 4x is 0, meaning I'm going to get y cubed equals x. Well, I'm basically stuck here thinking, well, for what values is this entirely going to work? For what values is x cubed equal to y, but also y cubed equals to x? Like I could see that 0, 0. 0 cubed equals 0. And 0 cubed equals, it works forwards and backwards. Basically, I kind of need mirror points. 1 cubed equals 1. And 1 cubed equals 1. There's one more out there. -1, -1. So these have become our candidates for mins, maxes, saddles, inconclusives will come from this. And these will be the points I test into my Hessian, into my D. Again, my Hessian matrix is going to be a double derivative of x. So this gets even simpler to just be 12x squared. But then if I took this same derivative with respect to y, I would get -4. Now, in case you didn't believe me, if I took this derivative with respect to x for my fxy, remember, my Hessian looks like this. So I'm working on a yx. I take my f sub y, and I'm going to take another partial due to x, and I would just get -4. Shocking. They're equal. Surprise. Wow. And now another derivative with respect to y. And so that D calculation would be that determinant. 144x cubed y cubed minus 16. And so if the concavity is not greater than 16, it will be a saddle point. If it is greater than 16, the concavity overcomes the twist and it will be min or max. And if they're equal, I can't really tell which one is more dominant, so it's likely a neither, but it's inconclusive. All right, so now we take our candidates and we test them out. D for the coordinate 0, 0. Well, when I plug in 0, 0, I get -16. And this is less than 0. Well, if this thing is less than 0, I know it has to be a saddle point, because the twist overcomes the concavity. Let's try another. 1, 1. When I plug in 1, 1, I get 144 minus 16. This thing is positive. But I still have to go check, hey, is this concave up or concave down? Because I still have to make that decision for mins and maxes. So I go over here to my second derivative of x. I plug in 1, 1, and I get back 16. So f double x is greater than 0. That means this thing is concave up. That means this thing is a min. Last but not least, check the coordinate -1, -1. -1, -1 actually cancels each other out, so I still end up with a negative, or a positive minus 16. So now I got to go check that second derivative. But the second derivative squares that -1. So it still ends up being positive. So it's still concave up. It's still a minimum. So that's the work that we do when we're deciding mins, maxes, saddle points in Calc 3. And you can see our beauty over here. That I have those nice two stark mins, a little bit in 1, 1, -1, -1, and you see that happy saddle point. This actually really looks like a pair of pants. This really looks like a saddle there as well. I can use this min-max idea in all sorts of ways. Like, what if I wanted to do the distance from a point to a plane? Like, there's all sorts of distances because the plane is infinite, right? The point from this moment up here down to my sheet of paper, you're thinking, well, I could draw a straight line down. Like, I kind of want to look for a perpendicular out of the plane to get to that point. Then I'm like following a path, trying to make a equation of a line and find its intersection with the plane, and writing a new parametric, right? There's other ways to solve this, but how about we just use the distance formula? You know what I'm saying? Like, the distance formula would look a little like this. Not y, z plus 2 squared. Keep pausing this video because I'm afraid of making mistakes and I should just really trust my gut. That's the truth. So my issue is this whole thing's kind of stuck in a square root. I don't want to take a derivative, a partial derivative of a function with chain rules inside a square root. Also, we've only been talking about x's and y's, and this thing has a z. So first, let's square both sides. And last but not least, let's sub out z, right? This is only just a distance formula away from this point. How is the plane going to get involved in this distance formula? Right here. Z equals 4 minus x minus 2y. And so that will get substituted in here. Instead of d, let's call this f of xy, because now it'll be a function of x and y. Hope you trust me on the 2 plus 4 is 6. All right, now I can min-max this function. Now I can just treat it as we've done with everything else. This was the little bit of work to get it to be a function of x and y, to use the distance formula that we know and love, to incorporate the information from the plane. And now let's solve. F sub x is going to be 2 times x minus 1 plus, ooh, this one's going to be spicy, minus 2, 6 minus x minus 2y. I want to set this thing equal to 0. All right. And this thing simplifies down just a little bit. If you're going to trust me a little bit here, 4x minus 14 plus 4y. And if I'm going to solve this for x, which I want to, negative y plus 7 halves. I hope you believe me that we can make those kind of steps there. Let's look at f sub y. In the same way, when I take my partial of y, it'll be 2y minus 4, 6 minus x minus 2y. And it's going to be 2 and 2. Yeah, I'm sorry. This is where, again, I'm second guessing myself and I shouldn't. I'll keep simplifying this thing. Where I'm going to get all right. Well, now I need to find a place where these two things are equal. And hopefully you can believe me that this is a line and this is a line. So if I want them to be equal, I need to find their intersection. And so I can either graph them or I can substitute across and solve. Something like this isn't so unreasonable. Then over here I could get like 4x equals negative 10y plus 24. Divide out x is negative 5 halves y plus 6. Since these are both equal to x, I can kind of substitute them in. I'm going to keep borrowing space down here, so I'm pretty low. This would be negative y plus 7 halves equals negative 5 halves y plus 6. I can solve this thing down. I can get 5/3 equals y. Again, jumping a little bit of algebra there because I believe in us. I believe in you to get there. And then when I plug it back in over here to get x, I would get, in terms of sixths, because my denominator would become sixths, 11 sixths. Well, yeah, and now if I wanted to go find z, I only have one relationship that compares x and y to z. So when I go plug this in up here and calculate again, a little bit off the page, 4 minus 11 6 minus 2 times 5/3. I promise you I get negative 7 sixths. and then you just the crowd goes wild. You can't believe it. Mr. P is such a genius. How did you do it? Oh my gosh. What did the question ask us to do, people? Like that was the most annoying part about this for me, is that I did all the work to get to my answer, and I just have a coordinate. 11/6, 5/3, -7/6. I'd actually have to go back and find it says find the shortest distance. Well, technically what I did is I found the closest point, but I didn't go find the shortest distance. So let me make sure that we go and do that. This is going to be like kind of bringing this guy right back over. When I do this calc, it actually does work out a little bit nice, if you believe me, that when I run this through the calculator, I get something like, let's just do a little bit of work together. Why not? This is going to be 25 over 36. This is going to be 25/9. This is going to be 25 over 36. I can multiply this by 4. 136. Or I'd get 150 over 36. That's definitely square rootable in a nice way too. If I got 25, that'd be 5 rad 6 over 6. How beautiful. All right, folks. Let's do this last one, and this last one is a bear, so I'll apologize now. I'm bringing out the pencil because I'm bound to make a mistake, because this is a toughie. But this is like where the real shit gets done. Talk about a real world situation. I have a box. I have 24 square meters of cardboard. Make the biggest box you can. Notice this box is going to have a lid on it. A lot of these examples sometimes have lids, sometimes don't have lids. Probably should have made that clear in the instructions here. But let's make a box with a lid. I want to maximize V. So I know I'm going to take V, and I know that V is length times width times height. But I also have this 24 meters squared of cardboard material, and that's actually going to come from the surface area. My surface area is 24, and my surface area, it's a bottom of a box, 2 length widths. It's going to be the side of the box, 2 length heights, the front of the box, 2 width heights. And just like in that last problem, how we had the issue of, I need a function of just 2 variables. My issue here is I have 3 and 3. So I'm going to substitute this over to get 2. In fact, I'm going to solve for the height, and then I'm going to substitute that height over. Like what I'm suggesting here is divide everything by 2. Factor out the h. And divide it over. This is shaping up to be a doozy, can you tell? So now I'm going to plug this in over to my volume, because now volume will be a function of just length and width, and I'll be able to min-max it the same way I've min-maxed all the other stuff. Let's have some fun here, folks. So when I plug this in, my new volume function is length times width times 12 minus length width over length plus width. Now I can take my partial derivatives. Like, let's start with a partial of L. Believe it or not, folks, this kind of stinks. Because I had to do a quotient rule, because I have L's in the numerator and denominator, I have W's in the numerator and denominator, we're about to have some fun, folks. Bottom D top minus top D bottom. Are you ready? Bottom D top. Minus top D bottom. One over bottom squared. Ta-da. And if I simplify this down just a little step here, I'm going to distribute on this side and work it out just a little bit. Did I make a mistake? No, didn't make a mistake. Sorry, I'm looking at the wrong side of my notes. This is going to be 12LW minus 2L squared W squared plus 12W squared minus 2LW cubed minus the other side 12LW plus L squared W squared. We haven't fun yet, folks. I got a 12 and 12 that cancels, thankfully. And the rest of it all kind of collapses. And if you look, it all has a common factor. W squared, W squared, W squared, W squared. So believe me when I take out this next step that says W squared, I knew that was going to happen, W squared times, these would combine make negative 1. We're going to start there at 12 W squared minus 2LW, because that's cleaner. Now I'll do the big bad one, the square, the 4th degree. It should come at the end anyways. That's going to be a negative 1. All right, folks. This is like a numerator-denominator issue. My denominator is never going to be 0, because if my box had the dimensions of 0, 0, it wouldn't really be a box at all. And I get the same thing actually out of my numerator. Now I get kind of two options out of this guy. Either W squared equals 0, which is useless, or I get 12 minus 2LW minus L squared equals 0. Pause. Hold on to this one. We're going to do V sub W, and guess what? We're going to get the same exact thing. Since there's a lot of symmetry in this function, we're going to get basically the same exact thing out of this, folks, where I'm going to have my L plus W times, now when I'm taking this derivative with respect to W, this is bottom d top, so this is going to be 12L minus 2L squared W minus bottom is minus top d bottom, and the derivative of the bottom is 1. So I've got this. So you can see how that symmetry is going to cancel. I'm still going to have my LWs canceling here and here. I'm going to have my cube come out here with the L's. I forgot my denominator. Trust me when I say that V sub W actually factors out to be the exact same, just switch the L's and W's. L squared 12 minus LW minus L squared over L plus W squared. And again, we have these two cases. Either L squared equals 0, which is stupid, or the other scenario, which comes out to be 12 minus 2LW minus W squared equals 0. Hey, if these are 12 is the same, minus 2LW is the same, the only way that these could both be equal to 0 is L equals W. That's the only way this thing is true. Typically, folks, this should give me some kind of edge into solving the rest of this problem. Typically, there should be some kind of leverage here that I get in the system of equations that allows this to cancel or substitute and solve. And technically, this will let me substitute and solve. Like now that I know L is W, I get 12 minus 2L times L minus L squared equals 0. Like that just makes 12 minus 3L squared. So that means L squared is 4. L is plus or minus 2. And again, extraneous solutions. Negative 2 is a stupid solution. So now I know length is equal to 2. I know width is equal to 2. So now it's my job to go find the height. Where can I go to find the height? The only relationship between L, W, and a constant, I can't do it over here. The whole point is that I'm maximizing the volume. So I'm going to go plug that in. 24 equals 2LW plus 2LH plus 2WH. That turns into 24 equals 8 plus 4H plus 4H. That means 16 is 8H. That means H is 2. So the best, most optimal way to make this out of 24 square meters is actually to get a cube. 2 by 2 by 2 is the best way to use 24 square meters of cardboard to make a volume of 8. How interesting. We'll learn more about this exact problem in the future. 30 minutes. Oh my God, that's way too long. 30 minutes, I'm so sorry.